In this video, we will thoroughly cover the topic of the full-wave rectifier circuit. After completing the theoretical information, we will create two different types of full-wave rectifier circuits using the Proteus program and observe them graphically. Let's start. What is full-wave rectification and why is it used? Full-wave rectification is the process of converting both positive and negative halves of an AC signal into DC. What are the advantages of full-wave rectifiers? Utilizes both halves of the AC cycle to produce a more stable and efficient DC output. The ripple frequency is twice the input frequency, making filtering easier. Applications: power supplies, AC-DC adapters, electronic circuits and devices. Now, let's examine the first type of full-wave rectifier circuit in detail. Bridge-type full-wave rectifier. Working principle. 1. Positive half cycle. Point A is positive, point B is negative. D1 and D2 conduct, while D3 and D4 are in cutoff. Current flows through D1, across the load resistor, and completes through D2. 2. Negative half cycle. Point B is positive, point A is negative. D3 and D4 conduct, while D1 and D2 are in cutoff. Current flows through D3, across the load resistor, and completes through D4. 3. Output. In both cases, the load resistor experiences a continuous positive voltage. The output waveform is rectified for both positive and negative half cycles. Advantages: no need for a center tap on the transformer. Provides a more balanced output. Disadvantages: requires 4 diodes. Higher voltage drop across diodes. Now, let's examine the second type of full-wave rectifier circuit in detail. Center-tapped full-wave rectifier. Working principle. 1. Positive half cycle. P1 is positive, P2 is negative. D1 conducts, D2 is in cutoff. Current flows through D1, across the load resistor, and completes through the center tap. 2. Negative half cycle. P2 is positive, P1 is negative. D2 conducts, D1 is in cutoff. Current flows through D2, across the load resistor, and completes through the center tap. 3. Output. In both cases, the load resistor experiences a continuous positive voltage. The output waveform is rectified for both positive and negative half cycles. Advantages: only 2 diodes are needed, reducing cost. Simpler circuit design. Disadvantages: requires a center-tap transformer. Transformer can be more complex and costly. Conclusion: full-wave rectifier circuits play a crucial role in converting AC to DC. Bridge-type and center-tapped rectifiers offer different advantages and are suited for various applications. The choice of circuit depends on the specific requirements of the application. Now, let's create the full-wave rectifier circuits in the Proteus program and observe the graphical results. If you enjoyed this video and want to see more content like this, please don't forget to subscribing to this channel. By subscribing, you'll stay updated with all the latest uploads and be part of our community. Don't forget to hit that subscribe button below the video. Thank you.